Good evening. I am Richard McGee, and this is the Learning Tree that you're watching. I have to my right Dr. Evan Hepler-Smith, who is at Harvard University. As a matter of fact, he graduated as an undergrad from Harvard University, got his doctorate at Princeton, and is now back at Harvard as a fellow. And how are you this evening, Evan?
I am very well, Richard.
Thank you for coming to be with me.
My pleasure.
All right. Today we're going to talk about the history of science, but before we get there, tell me a little bit about you, how you happen to be in this world, and how's it been treating you very kindly?
Well, it's been treating me well so far. We'll see
right.
how it goes forward, but it's treated me very well so far. I grew up in Pittsburgh, Pennsylvania.
Okay.
Had a great childhood there. Ended up going off, as you mentioned, to Harvard University for my undergraduate degree, where I actually studied comparative literature. So it doesn't have much to do with either history or science, although it does kind of connect with how I got interested in this field, and maybe we can get into that. But I studied literature, but I was really interested in the science. I loved introductory math and science courses. I took every 101 level science course I could take, and then I taught all of them after I had taken them. So I really loved science, but I really enjoyed my literary studies too. I graduated college and worked for a while, lived in New York, just kind of exploring different ways of maybe getting back into academia. I didn't know how I was going to do that, but then I discovered the history of science and ended up enrolling in a PhD program at Princeton.
You and I had a discussion, and I understand that both your parents are medical doctors, MDs, and how come they didn't lure you into the field of medicine?
Well, you know,
did they try?
If anything, they tried to keep me out of the field of medicine.
They tried to keep you out. They were successful.
I think. Well, my father is a real Renaissance man. He's a pediatrician by trade, but he's a man of very wide interests, and I think he always encouraged me and my mother as well to pursue wide-ranging intellectual interests. And when I told them that I was going to study the history of science, something that brought literary studies and historical studies and studies of hard science together, they were really excited about that.
No, very good. So you have now succeeded in fulfilling most of that job. So what are you going to do now when you finish your fellowship at Harvard?
Well, when I finish this fellowship at the Harvard Center for the Environment, where I am currently, I'm hoping to get a job teaching the history of science and history.
Think you return to Harvard as a professor?
Well, if they'll have me, I would love to really teach anywhere that'll take me. I love teaching, I love scholarship, and I'm hoping to, find somebody to pay me full time to do that in perpetuity.
No, good. All right, let's talk about the history of science. Let's talk about its history. How did this begin, and how very long ago? The history of science.
Well, the history of science, of course, goes all the way back to, you could say, even the dawn of human civilization. But the field of the study of the history of science goes back really to the early 20th century. And of course, there were scientists who, for a long time, had been interested in the history of their fields. Physicists who studied, Newton, chemists who studied Antoine Lavoisier and John Dalton, great figures, predecessors in their fields. But in the early 20th century, there was a Belgian gentleman by the name of George Sarton.
Okay.
And he had a little bit of a different idea. He wanted to study the history of science in the same way that historians of art study the history of art, or historians of religion study the history of religion. Sarton thought, that science was one of mankind's greatest cultural achievements, and that if humanity that is, better understood the history of this great cultural achievement, we would not only appreciate the greatness of the many human races, but might discover some common ground that could prevent humanity from being at each other's throats quite as much as they were. This was in the early 20th century during World War I, and then the interwar period. Sarton was exiled from his native Belgium during World War I and came to the US. So he was really preoccupied with finding a way to use the history of science to help bring nations, bring peoples together.
Right.
And he ended up at Harvard.
You do remember that it was not until the 19th century that the word scientist was coined by. You remember who that was?
By William Whewell.
Yeah.
Yes, Whewell was, yes.
And what did he do?
Well, William Whewell he's best known as a philosopher and a mathematician. He was a British scientist, a term he coined. But he studied all sorts of things. He was kind of a typical early, mid-19th century scientist in this way. He came from a well-off background, kind of at the upper levels of the social classes. He was interested in geology. He studied rocks and minerals. He was interested in mathematics. He was interested in natural history. He even wrote a book about cathedrals, the architecture of how cathedrals had been designed. So he, like many scientists in that period, really before science became specialized and professionalized in different disciplines, the way we know it today, Whewell, like many of his contemporaries, had wide-ranging interests and drew connections between what we think of as very different fields of knowledge.
What was the specific change in the way that the field was discussed beginning in the 18th century? In the 18th century, I understand that the field of science took on a more of a technical era. In other words, it wasn't rhetoric like religious rhetoric. And how did religious play a significant role in the science world before the 18th century?
Well, religion and science had always been very closely connected. The motivation of scientists, of course, as you mentioned, the word hadn't even been coined yet. They would have called themselves natural philosophers in the earlier periods, going all the way back to antiquity, but through the Renaissance in the 17th and 18th century. The reason that they gave for studying natural philosophy, how the world worked, was to better appreciate the master plan by which God had created it. And so by studying the movements of the heavens through telescopes, by studying the relationship between all different living species, people like some of people we think of as the greatest figures in the history of science, people like Isaac Newton, thought that they were coming to a better understanding of God's divine plan. So that was really a key motivation for the study of the natural world, for natural philosophy in that period.
Does that have an impact on all religions or just on Christianity?
It really is true of all religions.
It impacted all religions.
Absolutely. In fact, some of what we think of as the most important foundational developments in the medieval world, what we sometimes is described as the Dark Ages, although the medieval historians don't like to hear you use that term. The period in which European civilization was more fragmented in the 12th century, 13th, 14th century. Some really foundational discoveries in medicine and in mathematics, physics, were made by Arabic natural philosophers, living in Islamic natural philosophers, working within the framework of Islam, living in the Arab world.
Is it true that the 14th century saw the greatest changes and the greatest achievement in the science world?
Well, the question of what the most important period has been for the development of science.
What would you say the most important period was?
Well, one good answer is always the last 20 years, the most recent 20 years or so, because scientific knowledge tends to be cumulative. It builds on past knowledge. Sometimes it goes off in wildly different directions from where it had recently been going, as with Einstein's theory of relativity, kind of a very new direction for science. But in general, especially over the last 200 years or so, by any kind of metric you want to measure it, the number of people engaged in scientific and technological occupations.
Well, you just mentioned some things that happened in the 14th century. Were those the major and significant gains in understanding?
Well, a really important development in the 14th century that proved to be a crucial turning point for the development of science was the rise of the university.
Of the what?
Of universities. That is, of places where philosophers, natural philosophers, could come together, meet with other scholars, with theologians studying the Bible or or other religious texts and other religious traditions, and intensively work together on the project of advancing knowledge. We think of universities today as kind of one of the natural places where science is done. If you want to say, well, where are the scientists? You say, oh, they're at MIT, or they're at Harvard, or they're at Wellesley.
Okay.
And it was in this kind of late medieval period that universities, originally designed as centers first and foremost for the study of theology, but eventually increasingly places where natural philosophy and later science was a subject of more and more interest, they arose.
So tell me, how does this, is there a split between the natural sciences and the social sciences?
Well,
And how does that work?
there's, in a lot of universities today, there might be three divisions. There will be a natural sciences division, things like physics and chemistry and biology.
Okay.
There
Mathematics.
Mathematics is usually located
Physics.
there. Yep. The social sciences, things like sociology, economics, anthropology, sciences that study humans and human communities. And then the humanities, things like history and literature and music, departments that study the arts, works of human creativity. And there have been really interesting alliances and splits between those three areas over the years. There's a kind of a famous essay that a British social scientist wrote in the 1950s titled The Two Cultures.
Okay.
This guy's name was C.P. Snow. And he conjectured.
I've heard that name.
Yeah.
Yes. Okay.
He, it was really something that was discussed a whole lot just after it was written, and it comes up again and again when people talk about or are concerned about the increasing specialization and division in universities. In The Two Cultures, Snow argued that the humanities, which had traditionally been the area in which the upper class of British society had been educated, had become too separated from the natural sciences, and that people working in these two fields just couldn't communicate, couldn't talk across the boundary between the humanities and the natural sciences. Now, and this is, kind of what shows you how things aren't exactly the same way that they were today as they were for Snow in the 1950s. For Snow, the humanities was where all of the reactionary
Where was Snow located at that time?
He was in Britain.
Britain,
In the UK.
All right.
And he was writing about British society. So for Snow, all of the reactionary conservatives were in the humanities departments. Imagine somebody writing an op-ed in the Wall Street Journal today saying, oh, I'm tired of all these reactionary conservatives in our university humanities departments. But that was what he saw as the case. And it was really the liberals, people who had often come from a more diverse collection of social backgrounds, had kind of worked their way up through the ranks, who found places in the natural sciences in Britain at that time. And that political division, alongside the sort of division in the objects of study, the kind of methods that people used in the humanities and in the natural sciences, made the university a very divided place. And he was worried about that. He thought that that would stand in the way of progress in each of these fields.
Okay. How about some of the great names in mathematics? Who were some of those people who really stand out in developing in the mathematic processes?
Well, I think it's a name that's not maybe as well known as some in the history of mathematics, but a really crucial figure is a German mathematician named David Hilbert.
Okay.
He was a mathematician around the turn of the 20th century. He was famous for framing, I think it was 10 or so crucial problems that mathematicians had to solve, and I think maybe 7 or something of those problems have been solved now, almost 120 years later. So he really kind of knew what he was talking about when he thought these were the tough questions. But what Hilbert did was he made the field of mathematics a field focused on abstractions.
Ah, okay.
So he took
What is abstraction? Define that.
that is objects that do not correlate in any obvious way, don't derive from our experience of the world.
Oh, okay.
So not, if I look at these 2 mugs, I say, well, I can see 2 mugs. I think, well, I can tell the difference between just that mug and both together, 1, 2.
Okay.
This is how mathematicians for a long time thought about what mathematics was, right? It was a system for reckoning with the world based on human beings' sense experience of the world.
Didn't China play a great role in that, in the development of mathematics?
Chinese mathematics, you're getting me a little bit outside of my area of expertise,
Yeah, okay.
but they certainly did. Chinese science and technology was incredibly advanced, was in many ways far ahead of science and technology in Europe until about, the 16th century or so. This is a big puzzle for a lot of historians trying to explain why it was that China was surpassed in military prowess and in certain areas of science and technology by Europe during the early colonial period.
What is the state of mathematics today? Is it a area that is greatly needed and participated in, or what's the story on it now?
It is an area that is certainly incredibly important. Numeracy. People sometimes talk about numeracy in the same way that they talk about literacy.
Okay.
Right? It's a basic level of understanding. Almost, you can think of it almost as a civil right.
Okay.
That in order to participate as a full citizen in our society, you ought to be able to have a certain baseline set of mathematical skills that allows you to engage with important political questions and just to participate in our collective social life. That's mathematics at the level that kids are taught or ought to be taught in school, in primary and secondary school. As a research discipline, as something that professors at universities are sitting in offices and writing journal articles about, it is incredibly obscure. It is very hard to understand. Again, that's kind of the legacy of this moment I was talking about with Hilbert, when mathematics started to be about abstract ideas that are really not connected in obvious ways often with things that we can see and experience in the world. And there's a lot of concern, a lot of hand-wringing sometimes within the mathematics community about that. How do we make this abstract field make sure that people can appreciate it and support it and make it matter? How do we make mathematics not seem like something that only truly gifted people can engage in? That's a big problem in mathematics education today. We're on the learning tree, and there's a real concern, as I'm sure you know, about diversity and inclusion within the field of mathematics.
I don't know anything about diversity and inclusion. But that's a good way of putting it. I like that. Yeah.
Well,
because that's what we're about.
Yeah. There are a lot of one concern that people talk about a lot is women in mathematics.
Right.
All sorts of studies showing that at some period during primary school or maybe early in high school, sometime around adolescence, women, girls who are performing just as well or better than their male peers in mathematics suddenly their performance starts to drop off.
Is that right?
And
why is that?
People have come up with all sorts of explanations. Some people say, there must be some sort of natural explanation. It's just a fundamental biological difference in the brains of men and women.
Digression, huh?
I'm a little skeptical of that explanation, but I think that there's a lot of research. I have a good friend who's an educational researcher. She teaches 8th grade mathematics and tries to work on ways to understand and help support young women, girls learning mathematics. And there's a lot of kind of thinking that it might be this image that we've built up in our culture of mathematics as something that only truly gifted people can understand, as kind of different from a lot of other areas. Anybody can learn to read, anybody can write if they try hard enough.
Most people can
Most
learn.
people,
Most people can learn
you're
to
right,
read.
You're right.
Not all.
That's certainly
There are
true. That's
few
certainly
that
true.
just can't be taught how to
That's
read.
certainly true. But there's some research out there that suggests that part of the problem is how mathematics is treated as just an expression of innate talent rather than as a set of skills like any other set of skills that can be learned and practiced and kept in shape, or that can get rusty like any other.
How about chemistry?
Oh, chemistry is my specialty.
I figured that you'd get that one. Tell me a little bit. Who are the gurus in chemistry? Who are the people that's got the field moving, and have made great contributions in the world of chemistry?
Well, the list begins with a French chemist in the late 18th century named Antoine Lavoisier.
How'd you spell that?
Lavoiser. Is that an S-I-E-R?
All right.
Lavoisier, yeah, S-I-E.
Okay.
So Antoine Lavoisier, catching me off guard with spelling questions. I didn't know that we'd have a spelling bee here.
Okay.
But Antoine Lavoisier he was a really interesting figure. He was not only a chemist, but like a lot of natural philosophers, he had other occupations. He was he worked for the French state, the late regime French monarchy, in the final days of the French monarchy before the revolution. He worked for them in their tobacco factory. He worked on in their armory, in their arsenal, developing new gunpowder technologies. He was a tax farmer. He was one of the agents who went out and collected taxes on behalf of the French monarchs, which ended up getting him done in 1794 after. But alongside all of these other occupations, he was a chemist. And Lavoisier thought that the key to doing good chemistry was precision experiments, was getting the best instruments you could possibly get, the most precise balances, the best burning glasses, these big magnifying glasses that you could use to superheat chemical samples and combust them. And using these really advanced, sophisticated instruments, he was able to discover some interesting things. He discovered that when you burned a metal, it didn't lose mass, it actually gained mass. It got heavier when you burned it. And by observing that after combustion, metals gained weight, as well as a number of other very precise experiments, he came up with a theory that there was a insensible, invisible gas floating around in the air called oxygen, he called it. And there was another gas called hydrogen, and that combustion, burning, was a phenomenon in which this insensible gas, oxygen, got attached to things like metals or other substances that burned. Now, other people thought that this was a crazy hypothesis, and they came up with alternative explanations. There was a very popular theory at the time that actually burning was the release of a substance known as phlogiston. And people said, well, phlogiston has negative weight, and that's why metals get heavier when you burn them. So that was a little bit of a head-scratching explanation.
How has chemistry played a significant role in our society?
Well, there was a reason why Lavoisier got sort of the support of the French state to do all of these experiments. As I said, he worked in their gunpowder manufacturing unit in the arsenal.
Can we throw China in there as part of this chemistry makeup? Wasn't gunpowder developed in China?
It was originally developed in China. Yes, absolutely.
Yeah.
And in fact, China today, for very different reasons, is an incredibly important place where chemical research and chemical industry are based.
Looks like we got chemical factories all over the world now.
We do have chemical factories.
Developing the wrong kinds of chemistry.
Well, that's actually what I'm working on now in my research. I'm looking at regulation in the chemical industry. I'm looking at how toxicologists, people who study how chemicals affect the human body and affect the environment, and environmental regulators working for the EPA in the US or similar agencies in European governments and governments all across the world, how they keep track of all of the industrial chemicals that have been released into the world through the chemical industry. Well, it's difficult through a network of sensors and through analytical techniques, but more than anything else, through lists of chemicals that they are given by the chemical industry, the industry that they're supposed to be regulating, because those are the people who, the stakeholders in the process who have the best knowledge of what these chemicals are. And so it's a tricky situation, and I'm trying to kind of work out how it is that the kinds of information that environmental regulators and toxicologists have at their disposal.
Now, this is what your current research is.
This is what my current research is. But, but to go back to the importance of chemistry, its significance in the world, I like to think of chemical substances, let's say human-made synthetic substances, as performing about 4 key functions. Of course, there are millions of chemicals, but they all kind of do 4 or so things. You can use them to blow things up, gunpowder, enriched uranium, all sorts of munitions. You can use them to provide people with health, drugs, all sorts of chemical drugs, from natural substances distilled from plants, quinine from the cinchona plant, through sophisticated entirely synthetic drugs that we have today.
Internally, the body develops chemistry. Right?
Absolutely. Human bodies create their own drugs in certain ways. So that's the second thing. You can synthesize chemical substances to hold things, plastic containers, vinyl siding on houses. Yes, plastic bottles. And of course, the problem is that container often doesn't go on holding things. Sooner or later, it starts to break down, and where does that plastic go? And so that's why a lot of these plastic pollutants are such a huge environmental issue today, threatening wildlife all over the world. So that's the third. And then fourth, for pleasure, there are the wonderful, amazing, bright colors that were never seen on Earth until chemists developed them, synthetic dyes. There was a purple called mauve that was just revolutionized the French fashion industry in the late 1850s, early 1860s. And this dye was actually all of the chemical companies we have today, Bayer, the Bayer Corporation, DuPont, all of these chemical companies, really that whole industry in many ways got its start through making these synthetic, brightly colored dyes. And it's, of course, not just dyes, but there are all sorts of chemicals that are created for pleasure, materials of artists, recreational drugs, bring many things other than pleasure sometimes, but that's why they were created. So these are the kind of 4 purposes that I see chemicals serving, and each of them can be put to what we think of maybe as more noble ends or less noble ends.
Let's look at another field, a field that seems to pervade most countries: China, India, the Middle East. A bunch of countries kind of got involved in this whole process, and that's astronomy. So why was astronomy such a popular endeavor in so many different areas of the world?
That's a really good question. And it's true that astronomy is one of the most iconic areas of science. If you think of science, you think of Galileo and his telescope. Or maybe you think of the astrolabe, this fantastic, intricate instrument that astronomers would use to keep track of where stars were in the heavens. Now, astronomy was important in the ancient and medieval, early modern world for a couple of reasons. One of them was, as I mentioned before, the idea that by studying the heavens, we can better appreciate the design of the universe as a kind of way of understanding the divinity's, God's master plan, or the gods, plural,
You want to
depending on
repeat
what.
that? I find that interesting. Anticipating God's major plan.
You can appreciating the master plan
Yes.
of the gods in a
Is that a
polytheistic
God
society.
or gods with an S?
It can be either,
Plural.
depending on if it's a Hindu astronomer or a Muslim astronomer, or a Christian astronomer. But there was also a practical reason why astronomers would study the heavens. I think there are three reasons, actually, but the second is a practical reason. That is, they wanted to be able to make good calendars, and they wanted to be able to tell effective time.
Who made the first calendar?
Who made the first calendar? Ooh, I don't know if I can say who made the first calendar. There were all sorts of calendars, believe it or not, became the subject of bloody battles during the Reformation. There would be Catholic astronomers and Protestant astronomers, and they would come up with different calendars based on their calculations.
I think China got in there in that early period of calendars.
I believe it.
Yeah,
You
China
might
was involved in a lot of stuff.
All sorts of, again, as I said, a lot of areas of science and technology were developed to a.
Yeah, here it is right here. Chinese Sayers, for example, early developed a calendar and the methods of plotting the positions of stellar constellations.
Like the zodiac, for instance. Yes, really important. The stars were
Sorry,
incredibly
stumbling over my
important.
words there.
Oh, that's okay.
Little type is too little for me.
Well, that actually gets me toward the third really important use of astronomy, and that was astrology. Astronomy and astrology, that is the.
What is astrology?
Astrology is the discipline of predicting the future, predicting an individual person's future, what sort of occupations they might most effectively pursue, what potential pitfalls they avoid, what their unlucky numbers are, or predicting the future of nations is the Austrian, Holy Roman Empire going to win its battle with the Ottoman Turks, or are they going to lose their battle with the Ottoman Turks? Astrology was seen as an area of natural philosophy. It was an entirely legitimate field of inquiry that was closely linked, inextricable from astronomy. And so one reason that astrologers would study the heavens so carefully and try to plot the precise location of stars and especially planets is because, they had a formal technical system in which those specific positions of planets at the time of an individual's birth and then at future significant moments in their lives, they thought would give them clues as to the influence that these stars had on the future of this person's life.
So, now, how did they get all these figures that represent a certain month in the astrological calendar? Where did they come from? How were they designed, and what made the determination as to which those figures went, which month?
Many of them were derived from constellations.
From what?
From constellations, from collections of stars in the sky. But as to the association of particular signs with particular months, I've got to admit that I'm not totally sure how that developed. It's an interesting question,
How,
but
how
some of
about
it
how
has
about
to.
the names of the various? How about say, for instance, I'm a Capricorn.
Mhm.
How did I get to be a Capricorn? How did that period of time become known as Capricorn, or Eris, or some of the other names?
Yeah, I'm not entirely sure.
Yeah.
I can only assume that it must have something to do with particular constellations that are kind of positioned most prominently
Yeah,
in
probably.
specific places,
Probably, yeah.
specific times. So if you were talking about kind of associations between constellations and times of the year in ancient Greece, probably had to do with what sort of stars were ascendant at that moment in the Greek sky. And so
Okay.
forth, but this is all speculation. I don't know all the history of science, unfortunately.
That's fine.
Not
that's
yet.
fine.
I've got a
Now
few years to go,
I'm
though.
going to take you backwards now.
All right.
I understand that you once did some work in how you break down and name chemicals. I find that a fascinating subject. So let's talk a little bit about what you did in that research, in breaking chemicals down and naming them, and I think you even might have found one or two, right?
I don't know
or
if
named one or
I,
two.
well, I've named and unnamed a lot of them in my
You
research.
named a lot of them, okay.
But this was the focus of my dissertation, my thesis, as a PhD student, and I'm now writing a book about this process, about how chemists came up with ways of naming their chemical compounds. And this is particularly all of these synthetic compounds, these synthetic carbon-based organic compounds. They are called. And what I look at is how it was that in the end of the 19th century, the period of the rise of these big chemical firms that I was referring to before, firms that were closely tied to what was kind of the high-tech science of the day. You can think of it as sort of the nanotechnology, the Silicon Valley science of the end of the 19th, early 20th century. And the chemists working in these fields, whether in industry or in academic laboratories, started to run into a problem. And the problem was that they had made too many chemicals.
Made too many.
There
Okay.
were then, from what had been a few decades before, maybe a couple thousand organic chemicals derived from natural sources that they had known. All of a sudden, there were almost 100,000 different chemicals known. And what was worse, all of these chemicals were really closely related to each other. And so as chemists would name these things, these very closely related derivatives that they were creating in the laboratory, hoping that one of them might be the next blockbuster drug, might be the next aspirin, or the next mauve, super popular, valuable dye. They would name all these things, but they wouldn't know if what they were working on and had given one name to was entirely different from, or closely related to, or just the same as a chemical that their colleague down the road, or in Berlin, or in Paris, or London, or Baltimore had been working on. And so I write in this book in progress that I'm working on about how chemists got together to come up with a set of rules for giving a very precise name to every synthetic organic compound that would correspond in this piece by piece, unit by unit fashion to its structure. So if you've probably seen the structural formulas, these diagrams representing chemicals. If you've seen an Exxon Mobil commercial or any commercial for a drug company or chemical company or petroleum oil company, see all these hexagons with tails coming off of them, and some N's and some O's. And so these structures, each little piece of that structure would correspond to one part of a name. So you would have methyl for each of these little CH3 groups, and phenyl or benzene for that 6-carbon ring, fluoro for fluorine, chloro for chlorine. And so this group of chemists came up with rules for naming all of their compounds, and they got together in Geneva to do this. They went out to the opera. They had a good time. They brought their families. They got to talk about some matters of shared interest, which was really important for them at the time because the field was starting to specialize, and it was pretty rare that chemists studying sugars could come together with chemists studying alkaloids like morphine and quinine, chemists studying other substances, and talk about question of mutual interest. And then they sort of said, our job here is done. As it turns out, a really good way of getting everybody convinced that they need to come up with their own rules is to wipe your hands and say, we're done, we come up with our rules. And so what I discovered in researching this project was that the question of how to name chemicals effectively, a question that today, even to chemists, is seen as an incredibly dull, technical, tedious, boring matter. Was at the turn of the 20th century an incredibly central, pivotal question, a question with stakes that were extraordinarily high. Intellectually, how you named a chemical kind of conveyed certain ideas about what that chemical was, certain ideas about chemical theory, how chemicals related to each other. How you named a chemical could impact the way in which your colleagues were able to look up information about chemicals. The language in which you named a chemical might make it easier to look up and record information in German or in English or in French. So this was a matter of great kind of political significance for the organization of national chemical industries. Again, this was the early 20th century, the kind of high tide of nationalism just leading up into World War I, sometimes known as the Chemists' War, because of the importance of chemistry in warfare during that war, in manufacturing munitions, and of course in the first use of poison gases in conflict. And so I found that this question of how to name a chemical was not only a really significant kind of interesting intellectual problem in its own right, but actually gave me a way to tell in a really broad sense the history of chemistry in the late 19th and early 20th centuries, a period when chemistry was the queen of the sciences.
Let me tell you, let me see if I can get something here. Astrology, astronomy, and what are the other big names underneath the heading of natural sciences that are very prominent in the world today?
Well, today, maybe the one of the most prominent sciences. I mean, there, two, of course, are physics and biology.
Oh, okay. All right.
And physics and biology, it's interesting. You'll see an interesting thing will happen now. If you walk into a biology department and you talk to graduate students or kind of young faculty members, postdoctoral scholars like I am now who are working in biology, as often as not, you'll find that they didn't do their undergraduate degrees in biology. They did, they did them in physics.
Like you.
Yeah, well, like me, but
not exactly like you,
my path is a little bit more idiosyncratic. There's more of a pattern here, and in the life sciences, in biology, the pattern is that biology, the study of life, has over the last 2 or 3 decades become more and more focused on molecules, and especially on DNA, on genetics and genomics.
Yes.
And so the people who are doing new cutting-edge research in biology have often been trained in really computationally intensive fields, fields with a lot of mathematics and computer programming involved in them, such as computer science or physics. So, we're in the midst of a real transformation in what it means to study life, what it means to study biology. There are still plenty of biologists, of course, who go out into the field and dig up fossils and study animals, populations of animals. And I heard actually presentations from a couple colleagues of mine in the same center where I am today, one of whom was studying fossils of reptiles in Puerto Rico. She's a paleoherpetologist.
What?
A paleoherpetologist.
Okay.
She studies ancient lizards, but she studies ancient lizards because
Okay.
she hopes that in looking at how lizard communities kind of boomed and busted in the ancient world, when lizards went extinct or when lizard communities moved from one place to another. And by correlating that with changes in the climate and changes in human activity in these islands, she'll be able to use this data to help inform our predictions of what's likely to happen with biodiversity, with species and communities of species all around the world in an age of climate change and of increasing, drastic effects on the environment happening through human activity.
Now, we couldn't have this discussion without talking about the big man, Albert Einstein, who at least one of his theories has been debunked.
Which one is that?
Gravity.
How has gravity been debunked?
I thought there was an MIT professor who showed that things can go into space and can come back. Or am I misreading that theory?
That's interesting. I'm not entirely. I'm trying to think of the research.
Was
that
that
you're
the theory
mentioning.
that the professor at MIT had changed our thinking about?
I'm not entirely certain.
Right.
Certainly, some of Einstein's ideas have not turned out to have not played out. For example, Einstein believed that he was going to find a grand unified theory, a theory that accounted for all of his, kind of his own theories that he's best known for, special relativity and general relativity, which have to do with how matter behaves and space behaves on a very large scale, how stars move, with theories about how the tiniest bits, tiniest particles of matter behave, quantum mechanics and quantum theories. And he never managed to reconcile make the math all work out to bring these two theories together. But he certainly is responsible for a lot. He had 1 year in 1905 when famously he was working as a patent clerk in a patent office in Geneva, not even in a university, when he published 5 papers, each of which was a fundamental breakthrough and transformed the way we think about a different area of physics. So he was a truly transformational figure. He's one of the very few figures that you can really say, if he hadn't been around, you gotta think that science today would look different. Most of the time, I'm pretty skeptical of great stories about great men. Usually you cannot find somebody else who made quite a similar discovery around the same time, because different scientists or natural philosophers in different places were kind of drawing on similar sets of ideas. But Einstein was a truly creative figure. Einstein, possibly Darwin, you could say the same of.
Okay. Tell me, what is the meaning of pre-critical science?
Of
Pre-critical science.
pre-critical science.
Has something to do with stones and monuments, stuff of that nature.
Well, it might be a term for the ways that human communities had of trying to understand the workings of the world in prehistory. So, for example, the famous
That's
monument.
an odd name, like pre-critical.
Pre-critical.
Uh,
Yeah, I mean, it usually critique refers to reflection on knowledge. So, it might be that pre-critical science is a way of, thinking about the kind of methods that humans used to investigate the natural world, when they weren't thinking of what they were up to as this kind of study of how knowledge works, as this special, separate field, in the way that natural philosophers thought about natural philosophy, or scientists today think about science. But people have always been interested in the world around them. You know, in many ways, the kind of sophisticated science that people do with multi-million-dollar instruments in laboratories today is, you can think of it at the end of the day as trying to understand, figure out some little thing about how the world around them works. That, you know,
Tell me a little about what you do as a fellow at Harvard.
Well, as a fellow at Harvard,
You don't sleep all day, right?
I don't. I usually am pretty good at keeping myself awake, so I do a few different things.
Some teaching?
It's a good question. I do some teaching. I'm going to be teaching a course in the fall, this coming fall, called Environments in Crisis.
Okay.
And it's going to be a history.
Environment in crisis.
Environments in
Want
crisis.
to go there? That's a good subject.
It's, you know, it's a pressing subject today, certainly. What we're going to be doing, what my students and I are going to do, is look into moments in the distant past, but mostly in the recent past, the last 100, 200 years. Moments of crisis and disaster in which certain ways of understanding how science, technology, and the environment relate to each other got crystallized, got fixed. Certain kind of go-to examples for positive and negative relationships between science, technology, environment got kind of lodged in our collective consciousness, and, you know, we reach back to them to try to understand and, you know, predict what's likely to happen today.
So, how many, you going to teach one course or two?
This will just be one course. They take it pretty easy on me. It's a pretty cushy gig, this fellowship. I get a lot of time to work on my own research and writing, which is really exciting, and a lot of time, and this is really the point of the fellowship, to get to meet and talk with scholars, not only in the history of science, but in a whole bunch of different fields.
How far off is your book?
Well, I think it will most likely, the academic book publishing process is just the slowest thing you can possibly imagine. I think that my book will hit your local university bookstore shelves, I hope, sometime in 2019.
2019, okay. That's a long way off.
I know.
How many pages you got so far?
Too many. It's never, the challenge in writing, in scholarly writing, I find, is never having too few pages. It's finding a way to take 50 pages worth of material or 500 pages worth of material and cut it in half. Cut it down to 20 pages or 200 pages.
So, running back a little bit to the 17th century, what were some of the good things that happened in the 17th century? And why is it that we got all the way to the 18th century before we started talking facts and stuff that had been defined as identified, at least with some backing of evidence?
Well, you know, some great things happened in the 17th century. One thing that happened in the 17th century, at least partly in the 17th century, is the scientific revolution. Now, the scientific revolution is one of those terms that can mean as many different things as you want it to mean. You ask, you know, 5 historians of science what the scientific revolution
had a name to it. Then I'm trying to remember what the name was. That's something about. I'll think about it. I'll think about it.
Well, it
had a particular name that was given to it.
Well, there were a few transformations during the sort of late Renaissance.
Yeah.
You're thinking of the Renaissance and the through the 17th century, so in the 16th and 17th centuries. A few transformations in how natural philosophers investigated the world that make us historians think today of this period as a pivotal shift in
The date
how
of
science
the
works.
period of enlightenment.
The period of, well, the Enlightenment
Oh.
kind of came a little bit after. The Enlightenment
That wasn't the 17th century?
was the 18th century.
18th century. Okay.
Yes.
Well, I still haven't found my right word. I'll get the word.
We can talk about the Enlightenment as well.
Go ahead.
But the scientific revolution
Oh.
kind of has a few different threads to
Yeah.
it. And of course, none of them were, there's nothing new under the sun.
Yeah.
So none of these were entirely new in the 17th century, but they were general trends, shifts
Yeah.
in the practice of natural philosophy. One of them was a focus on sense experience rather than on texts. So there was a shift from trusting what you read in ancient books to trusting what you could see with your own eyes and experience with your own senses. Descartes was a kind of a well-known proponent of this view. He said, you know, if you don't
Good
experience...
philosopher.
Yep, the philosopher did. But he
Descartes,
was
yeah.
also a physician and also a natural. He was a natural
Yeah.
philosopher.
Yeah.
You know, like many of these figures. Again, he did all sorts of different things. So, the focus on experience, that was one shift. A second shift was the focus on doing experiments, the experimental method. That shift happened especially within new communities of like-minded natural philosophers who came together. A famous one of these groups was the Royal Society of London, a group of kind of aristocratic British philosophers who started getting together and doing experiments together to do things like try to figure out what was going on inside an air pump that led to all sorts of strange phenomena that happened when the air pump was pumped and all of the air was removed from that globe. And what this group of aristocratic philosophers decided was that they would get together and they would do experiments and collectively witness these experiments. And by being together in the same room, kind of operating under conditions of trust in each other, they were able to create reliable knowledge. They were able to create what they called matters of fact. That is, facts
Okay.
that they could all trust and continue to believe in. And so this was not only a shift towards a focus on doing experiments as a good way of doing science, understanding the world, but the beginnings of what we now see in universities or laboratories, that is kind of the idea that science is a collective process, that you want to get a group of people together, that the whole is greater than the sum of its parts. There were a few other transformations during that period. I mean, especially the discovery of all sorts of new flora and fauna in the age of exploration, when European explorers started going
But the
to
reliance
North
was
America.
more on empirical data and instead of a theory or a concept,
Yep.
which turned us into a whole different chapter of scientific achievement.
Absolutely, it certainly motivated. One important aspect of that was that it motivated people to start collecting a lot of empirical data, and of course that gets more people involved in the enterprise of doing science, which triggers a whole sort of cycle of increased engagement and activity in these fields.
Well, Evan, you got any more good things there you want to tell us before we close out our discussion?
Really, I'd just like to say I don't have a book to plug yet, as you know, because it's not going to
I
be
know.
published until
You
2019.
just told me. 2019, okay. I
but-
think they'll let me hang around this studio to 2019.
I expect to be back here in 2019 with my book, and we can talk about it.
All right.
All right.
Well, again, I thank you for joining me. This has been a good conversation. And I'm sorry I don't read very well, but I've got to learn how to print stuff that has bigger type.
Well,
That always gets me, trying to read this little type, But thank you.
thank you very much, Richard.
Yes, and I want to thank my viewing audience. I hope that you get a little something out of what we've just discussed. And keep looking. I'm Richard S. McGee, and this is The Learning Tree. Good night.